Hello, class. Welcome to your lecture on lean systems. I think you're really going to enjoy this after all that you've learned about operations so far this term.
Well, as it turns out, this is a great chapter just in terms of its content being really current and important to business. But it's also, if you think about it, it's a good chapter to think about our course as a whole, too, because when we start thinking about lean systems, we're talking about an approach to operations that really is a complete system. It spans all of what you're doing in operations, everything from your strategic perspectives on customers and your way of organizing your shop floor, if there is a shop floor, your way of using employees to make improvements, and all the way down to things that you might think about in terms of order quantities and how you schedule and so on. A real common focus in lean is to eliminate waste, and waste reduction is a big issue. So anyway, let's jump into it. Your book says that lean systems are operation systems that maximize value added by each of the company's activities by removing waste and delays from them. Delay would be a form of waste. So when we say value, we're really talking about something that a customer considers value. When you go to the grocery store and you check out, it seems like the natural thing to do is for the person at the register to put the items that you bought in a bag. Well, if you can carry that without a bag and you don't value the bag, in fact, you think the bag is something you're going to have to deal with when you get home, then the approach of lean would be to not require you to take the bag, right? Because you don't think that's valuable. In fact, if we found that none of our customers actually valued having a bag, then we would get rid of the whole aspect of having a bag for groceries. It's a simple, silly example, but you get the idea. A lot of times you go through, to give you another example, you go through the drive-thru at Chick-fil-A, it's summertime, you want a peach shake, or it's wintertime and you want what do they have in the winter? Peppermint shake, something like that. Yeah, pretty good stuff. Anyway, in my experience, they're going to ask if I want a cherry. You want a cherry and whipped cream with that? If I'm one of those people that thinks it's kind of weird to put a cherry on a peach shake, then why would they put the cherry on there before they give me the peach shake? So that's just sort of the example when we're talking about value. So lean obviously has many tools and concepts that would apply in manufacturing and services, but one of the ways that we see lean is by limited use of inventory. So obviously, if we're thinking about inventory and its limited use as part of the definition, then that might have us thinking more in terms of manufacturing. Another thing that might have us thinking in terms of manufacturing is the fact that the whole idea of lean grew out of something called just-in-time production. Another word for just-in-time production is the Toyota production system, because that's where it came from, and that's the classic full-blown sort of implementation of what JIT is, and it's the source of the lean philosophy and what we mean when we talk about lean systems. So the JIT philosophy is basically the belief that waste can be eliminated by cutting unnecessary inventory or capacity and removing non-value added activities in operations. The folks at Toyota that developed this JIT approach and their colleagues in their supply chains identified 8 common types of waste that they would try to eliminate. So the Japanese word for waste is muda. Muda is what we're trying to eliminate. First was overproduction. That's making components or parts or items before they're needed. What happens if we make something before it's needed is it sits around for a while and we don't know that we created problems. So, let's say we're making, let's make it simple. We're a bakery and we're baking cakes for our customers, and they're going to show up through the week, and we bake on Sunday and they eat cakes through the week. Well, sooner or later, a customer comes in and says, your icing was really kind of grainy, and as a result, I thought the cake was not really what we needed for our setting. Well, it's been days since you made the cake. You don't know why that icing is grainy. If you made cakes a few hours ahead of time, then you'd be very quickly able to respond. And in the meantime, you've got 4 days worth of cakes still sitting there that you haven't sold, and you got to go figure out which of these have the grainy icing. Did they all have grainy icing? I have customers that are never going to come back. So overproduction. Inappropriate processing is using high sort of precision equipment or complex, fancy equipment when simpler machines would suffice. So what happens is we end up putting money into something, getting something that's very specialized and specific and difficult to keep up with and understand how to use and all that kind of thing, when we could have gotten by with just something that's old, that's maybe even used, that would accomplish the task that we're looking for. So, yeah, we understand what that is. We've probably, all of us probably have appliances in our house with a lot of characteristics that we're never going to figure out how to use even. And that may be true for our televisions. I think I have a television, that's so-called smart television, that has a lot of features that I'm never going to use. Waiting, a delay, is not, it doesn't add any value for a customer. So when we have a production facility where workstations are not balanced, then some workers have to wait for others to catch up, and that's obviously wasteful. Transportation, excessive movement. If our storage areas are far away from the work centers where the materials are used, we can damage stuff while moving things. Plus, we got the cost of moving them. Doesn't add any value. Motion, needless motion. So. If your workers are going home at the end of the day just completely exhausted, it might be because the jobs are designed in such a way that they have to do a lot that they wouldn't need to be doing. So extra bending, stretching, reaching, lifting, walking, excessive motion could be a form of waste to be eliminated. Inventory gets a lot of the attention. Now, like we've said, with overproduction, excess inventory hides problems on a shop floor. Plus, you got to, pay to heat or cool the space where it is in a lot of cases. It can increase lead time just simply because it's in the way. And so there are a lot of problems associated with having too much inventory that we might prefer not to have. Obviously, inventory is helpful. We're going to need some, but we can't have too much. Defects are obviously a waste. If you spend time making something and it has no economic value, then you've wasted your time. or if it has some economic value but requires further processing like rework to make it have that value, again, you've wasted your time. Or if because you make defects, you've got to have inspectors, that's a waste. So lots of ways to think about defects as wasteful. And number 8 is one we don't think about a lot. It's not what it sounds like. Underutilization of employees, you would think you're saying your employees are not busy enough. But really what this drives at is the fact that employees are not machines. They come with a mind. They come with creativity. Why hire someone to do what a machine could do for you is a question you might ask. Why don't you pay your workers for their ideas and for improvements that they contribute to your process? So that's what we're talking about when we talk about underutilization of employees. Just yesterday, I got an email from a former student who's an associate vice president for continuous improvement at a large American organization. And it's interesting what he said in that email. He said, a really common metaphor that a lot of times we use when we're thinking about lean systems is the analogy of the river and the rocks, or the water and the rocks. So in this analogy, the water is inventory. And like I said a few slides back, inventory can really help us to operate our systems. If we have a strike at a supplier and we have inventory, that's no problem at all. If we have bad parts shipped from a supplier or made in our facilities and we have inventory, we can just put it aside, get a good one, and keep on going. So inventory is something that helps us to operate our system even when there are problems embedded in the system, disruptions in the form of any kind, whether they're quality related or related to overt acts by employees or poor scheduling or whatever. All of those things can be accommodated if we have inventory, and we might still meet our schedules. However, in this analogy, there's not just water, there are also rocks. And so the rocks are the disruptions, the kinds of things that we've been talking about. If you have a lot of inventory, you may have very little information about the rocks. You may never see the rocks. And as a result, you're unlikely to remove the rocks, which are obviously waste. So when we think about lean, we do want to have enough inventory for our system to operate. We want the boat to be able to float down the river, but we don't want to have so much inventory that we never see what the rocks are and we never make the channel better for boating, so to speak. A common story is told about a retired from large U.S. auto manufacturer individual who went to work for Toyota as a senior manager at their production facility in Kentucky. At the end of the day, a Japanese manager and he were walking back to their offices from the plant floor. The American manager was complaining about how difficult the day had been. They'd been out on the shop floor solving problems all day long. Nothing seemed to have gone well. In his mind, it was a bad day. But the Japanese manager had the opposite view. So, this is a fantastic day. We know that with thousands of parts and hundreds of operations putting together, assembling a car, we know there are going to be problems. The days that are bad from the Japanese manager's perspective are the days that we don't see the problems. And so he thought it was a great day because they were able to find and eliminate problems that were present in the assembly process. And that goes right along with this analogy. So you, from a lean perspective, don't want to have too much of the water, but just being realistic, you can have too little water and not get your boat down the river or not get your orders to customers. The good thing that inventory does for us is it decouples an operation from another operation, and thus it gives us insulation from problems that occur elsewhere. So we've got to have some inventory to protect us. In the news these days, we frequently hear about situations where manufacturers are having to shut down. For example, in the early months of 2021, we see auto manufacturers with a shortage of chips having to shut down. And so, if they had enough inventory, perhaps they could continue to manufacture. There's this balance that we talk about. If we're going to be lean in regard to inventory, we're probably going to need to make some changes in terms of a lot of things, and that's why we call this lean systems, and we're looking at this from a systems perspective. For example, if we're an auto manufacturer and we're operating under this lean philosophy, and we have a plant where a unionized workforce is disgruntled, they decide to go on strike. Maybe what they made was steering wheels. We don't have any steering wheels. We don't need any of the other parts that go anywhere into the car, and the whole assembly line and the whole supply chain really gets shut down. So a lot of leverage the employees have there. Well, yeah, our approach to employees better be different than the normal adversarial approach that we might have seen in the past, or we're going to end up with a serious business problem whenever there's a minor labor problem. Similarly, we might have a supplier that, for some reason goes bankrupt. Well, no, we need to have a different approach than an adversarial approach to our suppliers. We need to have an approach that seeks the success of our suppliers, because we need reliable suppliers rather than having to carry inventory. So you see that this lean philosophy needs to be it needs to be used and interpreted in a systematic way, in an ideal sense. In addition to those better relationships with suppliers and employees and even potentially customers that are important in the lean system, in the just-in-time system, it's important to have small lot sizes so that you have less inventory, so that you're not doing this overproduction thing. And of course, you'll recall that a smaller lot size would require smaller setup times. The economics that we explored when we were talking about lot sizing with the EOQ is legitimate. I mean, if it costs you a lot of money to set up to produce or to place an order, you can't be doing that every 2 hours or every hour. You need to order a good bit of inventory to justify that expense of placing the order or setting up to produce. So one important aspect of lean production and JIT systems is working to reduce setup times or setup costs. And there's a gentleman who worked with Toyota and later the Japanese Ministry of Industry and Trade. His name was Shigeo Shingo, who made the claim in the 1960s that any setup in any industry, anywhere in the world, could be done in a matter of minutes. And so now there's this terminology called SMED, stands for Single Minute Exchange of Dies. And he's demonstrated that this is true. If you read his books, you'll see tables where original setup times across an industry around the world were reduced by a ratio of something like 22 to 1 or 17 to 1, this kind of thing, depending on the industry. You see a lot of case studies where setups that might have taken 8 hours are now being done in a matter of minutes. And you might think, well, that's just absurd. How could that possibly be the case? I mean, if you're really interested in it, then you might do some research on the SMED system. Not so much rocket science as thinking about the setup process and what can be done while you're still producing, and how you can streamline what's being done during the period of time where you're actually involved in a changeover. There's a link on this slide that might be fun for you to watch. It shows the impact of setup time reduction, if you can call it that, if you're going to let us call it that, in automotive racing, sort of a Formula One example. It's pretty entertaining to watch. You might just take a break, give yourself a few, it's a 2-minute video, so just give yourself a few, take a look at it, and you might enjoy watching that. So that's the YouTube video. The link is on this slide. Anyway, thinking about that, the key is if you reduce the setup times, then you're able to reduce what's economically feasible in terms of lot sizes. And your ideal would be to get to a situation where your lot size conforms with the rate at which the product is being used, and that would be like a maximum quantity. And you could say that the ideal lot size really is 1, produce 1 when it's needed. So if you view holding costs as onerous, and more importantly, if you are able to reduce setup times, then you're able to encounter a situation where you can produce regularly in very small lots and match the production rate of components with the rate at which they're used in subsequent processes. That rate at which they're used in subsequent processes is oftentimes referred to by the German word takt, T-A-K-T. So takt time is like a drum beat, and we would like for all supply processes to be operating in takt time. And takt time, ideally, would reflect a level master schedule where maybe we're doing the same thing every 2 hours, or every day it's the same product mix. And that way we're actually producing whatever a customer wants very close to the time when they might need it. So that's sort of the idea of having an even flow. And you're thinking about that river in the rocks with not much inventory, just enough for this period of consumption being produced all the way through the supply chain at the same rate at which the material is being consumed. So if we can do that, then we might be able to do something more like a pull method of workflow, where instead of making large batches of items and putting them on the shelf to be used as needed, we're able to see what was just recently used and replace that. So we'll talk later in this slideshow about a Kanban system that shows you how that would work in a lean scenario. Another systematic issue that's important is to make sure that quality issues are addressed at the source. So the Japanese word for this is judoka. And what that means is when an operator or a machine senses that there's something wrong, maybe they see a defect, maybe when they're installing, let's say, a dashboard onto a car frame, it's supposed to click in place just naturally, and they all of a sudden they realize they had to kind of force that to fit, and they didn't hear the click, it didn't feel right. Then they have the opportunity to shut down the process, identify what the actual problem was, have people, because the process is shut down, come and help them solve the problem and make sure it doesn't happen again. Might even design a Pokayoke, which is a mistake-proofing device to ensure that the problem doesn't occur again. Something like that. We'll find a countermeasure that's effective in some way. So then, really what we're looking for in terms of the system from a production perspective is having uniform workstation loads operating essentially at takt time, as we described on a previous slide. And so, the idea is that the load and volume and product mix is something that is a recurring thing that's stable and even across the entire system. It allows us to potentially even have something that we refer to as mixed model assembly, in which case, we end up with a single assembly line producing multiple items based on materials being fed from supply workstations and from external suppliers in the order in which they're needed for the assembly that is to be done next. And so that's sort of the idea that we're working toward. And again, we don't want this unnecessary processing. So to the extent we can, we use standardized components, and if there's an off-the-shelf available component that's going to work just fine, why should we design a similar item for specific unique application? And why should we have a special fancy machine if there's a machine off the shelf that'll work fine for our purposes? So we're trying to keep things as simple and repetitive as we possibly can. We'd even like for our workforce to be flexible, and this helps with that, but we'd like for our workforce not to be pigeonholed into very narrow job descriptions where they cannot sort of rotate around and provide the activity, the service, the function that is required most at a given point in time. 5S, making sure that there's a place for everything. Everything's in its place. The workplace is clean and orderly and maintained in that regard. It's a very positive thing, very helpful in a lean system. It eliminates a lot of waste associated with disorganization. In a lean system, automation is actually seen as a positive thing. I know there's a lot of negative baggage associated with it. If we're thinking about automation in our country, a lot of times we're thinking about losing jobs. But the other way to think about that is if there's a job a machine can do, why would we ask a person to do that? Wouldn't it be better to let the machine do that and use our employees' creativity to improve the way that we do things? So, there's this view that we may be underutilizing, again, our employees if what we're doing is we're just paying them to do some routine task repetitively that a machine could obviously do with less fatigue and eventually less defects and less errors. Finally, it's important for us to use something called total preventive maintenance, and actually we might even say total productive maintenance. So the idea is that all workers would have responsibility to do the basic maintenance on their equipment, but we would like to ensure that preventive maintenance is done at regular intervals or even productive maintenance. So a machine may not be at a point where we need to do preventive maintenance to keep it from breaking down, but it might be at a point where we could perform some maintenance and it would be more productive. And so, those are important considerations that we might think about as we consider the sort of systematic aspects of lean that will enable us to lower the water level and not have to worry as much about the rocks. This is a famous graphic here. It's in the original book published, translated into English, written by a guy named Taiichi Ohno, who is a major leader at Toyota during the time that the Toyota production system, or as we say, the just-in-time system, was being developed. And in his book, he has this figure, and he says basically there are three main pillars. And this is sort of a description of the system. And we've seen all of these elements as we've been talking our way through. This kind of gives a brief, again, summary and review of what the lean system or the Toyota production system or the just-in-time system involves. And so what we're looking to accomplish is to generate the highest quality at the lowest cost with the shortest lead time by eliminating waste. And the first pillar, the left side green pillar, is labeled here as just in time. Essentially, could be referred to as quantity control. And so here we're thinking about those aspects of tack time, one-piece flow, pull system, which is much associated with that Kanban system we're going to talk about in a few minutes. And then this culture of continuous improvement. So not underutilizing employees, but creating opportunities for employees to use their creativity and helping them to learn how to be more creative so that we have people come into work seeing their job as improvement related and not just as widget related. And then Jidoka is sort of related to quality control, you could say. A bad part that you get just in time is not in time. And so these issues of being able to stop the line, error proofing with Poka-yoke, having visual indicators that easily indicate when there are problems, separating operator activities from machine activities that could be automated. Those aspects are the third pillar that we might talk about. Underlying it all is sort of productive maintenance, supply relationships that are stable with suppliers and customers, using a standardized approach to defining work, and this idea of Hijunka, which has to do with leveling the production load. So that's a summary of the system. Let's look at a couple more sort of issues or things that we see in the system, and we'll be done with this. We want to look at group technology, and we want to look at the Kanban system, and then I think we'll be done with this chapter. So the idea of group technology is something that goes along with cellular manufacturing. And what we like to do a lot of times in order to have more flexible workers is create production cells that produce a variety of parts, but using a uniform routing. And in order to do that, we need to design the product in such a way that it can be made in the cell, and that's what group technology is talking about. So instead of having a job shop with large lead times and large batch sizes, what we can do is we can create a cell that produces a variety of things using the same resources, but produces them in small quantities because we've designed the parts in such a way that the cell can make them. And we've designed the cell in such a way that it can make this variety of parts. Then we have a lot of flexibility. If the cell's really busy, maybe we put 2 workers in the cell. Or if the cell's not as busy, maybe we have 1 worker and he can control all of the equipment at the same time. So this shape, the U shape, is very common when we start thinking about that manufacturing approach that we would call cellular manufacturing. And the underlying product design approach is called group technology. So if we think about how a job shop might have looked, it looks sort of like the spaghetti diagram on the top left, where jobs have routings, but they have to wait to access resources as they move through a larger, maybe operating facility, and we produce things in larger batches. Instead of having work centers like lathing, milling, drilling, grinding, and assembly completely separated, what we could do is create a job cell that has all of those resources in the cell. And that way it's capable of making the entire mix of items that are in the product group that we've designed. Now, the last topic in this chapter we'd like to talk about is the Kanban system. Kanban is a Japanese word. It means card, like you're playing a game of rummy, you're using cards, you're using Kanbans. Another way to think about it is it's a visible record that can be used to control the flow of materials through a facility. I think it's also a Chinese word that sort of has this notion of being a poster that conveys information, something like that. Obviously, it came out of Japanese in this context. So we could have one-card Kanban systems, two-card Kanban systems. There are a variety of different approaches. But basically, what the Kanban does is it provides authorization for someone to do something. So an empty container could be a Kanban. So here you see assembly line 1 and 2, and you see a fabrication cell. So if the assembly line sent an empty container to the fabrication cell, that could be a single card Kanban that says, fill this back up. It would need to have on the container what goes in there and how much goes in there. So the fabrication cell would simply replace what had been used by the assembly line. It's also possible to have disposable containers like cardboard boxes or something like that, and for a card to be pulled off of the disposable container by the assembly line. And then the card goes back to the fabrication cell, indicating that they need to replace what was used by the assembly line. So the container doesn't come back in that case. The card makes its way back. You'll see it working in the next few slides. So in this scenario, the assembly line has used some material. It's sent back empty bins, and the cards have been taken off the bin, put into a receiving post or an inbox at the workstation. And so they pick up a card, put it on a container, and go to work. They make what the card authorizes them to make, put it in their outbound stock location, and of course then it gets used by workers at the assembly operation. And we pick another card and make whatever it is that authorizes us to use it. It gets used at the other assembly operation. So essentially what's happening is these containers and cards are just making the loop from the place where inventory is used of a particular description back to the place where the inventory is fabricated. And so you basically, simple rules are going to operate it. You don't make things unless you have a free card that's authorizing you to make them. You don't use things that are not associated with the card that you're authorized to withdraw, or the container that you're authorized to withdraw from. And always when you withdraw inventory, you send a card back. So you might ask, well, who decides how much of what to make when? And the answer is, well, the cards really communicate how much to make when. But we do kind of have to think about how many containers or cards of a particular type do we need, and how many units should be held in each container. So the number of units is really a lot size thing, and the number of containers is really a reorder quantity. And so essentially what's going on is something like a queue model that we talked about in prior classes, where the reorder point is basically the point at which we empty a container. And so you could say that a reorder point model is what's being applied, only instead of thinking about using it with large quantities, we're thinking about using it with very, 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 very small quantities. So that sawtooth diagram that we saw back in our inventory chapter, it's not working with quantities that might last us over a period of several days or several weeks, but it might be working with quantities that last us 15 minutes. And so the movement of the cards sort of automates the reordering so that we don't spend a lot of management time figuring out how much to order and when. No, we figured it out ahead of time. The reorder point model, we could say, utilizes something called Little's Law, and that's also what's in place here. So generally, Little's Law is applied to queuing systems or flow systems, and flow is what we're looking for in this scenario. So basically, Little's Law says that the amount of work in process inventory we have is equal to the average demand rate multiplied by the time a unit spends in the manufacturing process. Well, that's how it's applied here anyway. And so there's a formula that reflects that helps us to know how many kanbans we might have in a given loop. This is that formula. I might start with the form of it that says Kc is equal to d bar times the quantity w bar plus p bar times the quantity 1 plus alpha. So d bar times w bar plus p bar is essentially the average demand rate times the time between when a card is moved to a card bin and the production associated with it occurs. So in other words, it's the time from when a withdrawing workstation sends back a card until it receives the replacement. And you could say d bar times w bar plus p bar is like d bar times L, which we had in a reorder point model. And you'll notice that's multiplied by 1 plus alpha. So the 1, d bar times L bar times 1, that's like expected demand during lead time. D bar times L times alpha, well, alpha is a safety stock factor. It's a policy variable. Basically, that's how many extra cards, how many extra units we're going to have on hand when we place our order. And so if we simply divide that formula we've been talking about by C on both sides, that'll tell us the number of kanbans that we need to have in a particular loop in order to ensure that when we withdraw some inventory, it'll be replaced with a degree of confidence that we're satisfied with before we have to withdraw some more. Here's an example. Westerville Auto Parts produces rocker arm assemblies. A container of parts spends 0.02 days in processing. It might be more common to convert that to minutes. And 0.08 days in material handling and waiting. Again, could be minutes. Daily demand for the product is 2,000 units. So we could make that minute by minute demand or hour by hour. Key thing is to have units consistent. We want 10% to be our safety stock factor. So if each container contains 22 parts, how many containers should be authorized? And then they want to know, suppose that a proposal to revise the plant layout could cut materials handling and waiting time per container by, in this case, 25%. So how many containers would be needed? So it's pretty straightforward. Let's look at it on the next slide. Of course, if you have the numbers, the calculations are pretty straightforward. Here, we've got 2,000 is the daily demand rate being multiplied by the wait and production times, 0.08 and 0.02 days added. And that, of course, is multiplied by 1 plus 0.1, which is the 1 for the expected demand during lead time, plus 0.1, which is the safety stock factor. Divided by 22 units in a container tells you need 10 containers. So you have 10 containers going in the loop based on that information. It's the same arithmetic if we reduce the waiting time to 0.06 days. So, in that case, we do the same arithmetic, we end up with 8 containers is what's needed on the loop. We alluded to this earlier in the description of Kanban, but the container itself can work as the signaling device, and we can even have situations if the using workstation is very close to the producing workstation where we don't even use containers, but just designate a physical space as the signal. So if the physical space doesn't have any inventory, production's authorized. If this physical space has inventory, production is not authorized. So a painted square on the floor is an easy example of that kind of thing. I'll just say your text does have content in it related to value stream mapping. That's a very useful tool. It's not necessarily so associated with lean production as just a valuable tool for understanding processes. It's not something that's in the scope of what we want to do in this chapter, so we'll skip over that part of the chapter, and the rest of what's in this slideshow is simply end of chapter solved problems that I put here just for your convenience, so you don't have to go digging through the book in case you're just looking for an example. Hope you enjoyed the slideshow. Take care. I've enjoyed this one too.